Imagine you're trying to predict house prices based on size. You look at some past data and think, bigger houses cost more. So you draw a line through the points. But here's the problem. Someone else draws a different line, and someone else draws another. All of them look reasonable. So which one is correct? This is exactly what we do when we rely on intuition. Our brains are great at patterns, but terrible at consistency. Now imagine this isn't house prices, it's medical risk, or stock prices, or loan approvals. A small change in judgment can mean a huge real-world impact. Machine learning libraries solve this with one line of code. But if you don't know what's happening inside, you don't know why a model made a prediction. You can't debug it, you can't trust it, and you definitely can't improve it. So what we really need is three things: a clear rule for drawing the line, a way to measure how good the line is, a method to find the best possible line, not just a good-looking one. And this is exactly where linear regression comes in. To understand linear regression properly, we're going to work with a very small data set. Not thousands of points, not fancy data, just enough to see every step clearly. Here, X represents house size and Y represents house price. These numbers are small on purpose, so we can actually calculate everything by hand. Let's plot these points. Each dot represents one house. Already we can see a trend. As size increases, price generally increases. Our goal is to describe this relationship using a straight line. Not because the world is perfectly linear, but because a straight line is the simplest model we can start with. But here's the key question. Which line should we choose? And more importantly, how do we choose it mathematically, not by intuition? To answer that, we first need to define what a line actually is in math. That's where we go next. Now that we have the data points, we need a rule that takes a house size and gives us a predicted price. Linear regression starts with the simplest possible rule, a straight line. This is the entire model. For any input x, the line outputs a prediction y hat, meaning predicted y. Let's break this into two parts. First, b is the intercept. It's the value of y hat when x equals 0. So b decides where the line starts on the y-axis. If I increase b, the whole line moves up. If I decrease b, the whole line moves down. Now the slope, m. This decides how steep the line is. If m is large, the line rises quickly. Price increases a lot when size increases. If m is small, the line rises slowly. So m controls the tilt and b controls the vertical shift. And here's the big idea. Every choice of m and b gives a different line and a different set of predictions. Now that we understand the equation y equals mx plus b, the real question is, how do we actually find m and b? There are two main ways to do it. One is called the method of least squares. The other is called gradient descent.